The next big topic that we need to talk about as far as sequences are concerned is whether or not the sequence is monotonic and or if it is bounded. So bounded above and below just means that there is a number either always bigger or always smaller, depending if you want to look at bounded above and below. So if, for example, I have 1 over n. So 1, 1/2, 1/3, 1/4 is my sequence. This sequence is bounded above by 1. It's also bounded above by 10. It's bounded above by a couple other different things, but bounded above by 1 is the most important. It can be equal to a number in that sequence, but we're bounded above by 1. We can also show with limits that we are bounded below by 0, and so we say that this sequence must converge. The sequence is bounded above or below, which means it's a bounded sequence. If you look at increasing and decreasing, then this gets us into whether or not we can converge. So if you have a bounded sequence and you know that the sequence is either monotonically increasing or monotonically decreasing, then you can show that the sequence is convergent. Now, what does it mean by monotonically increasing and decreasing? That means that once you get to a certain point, that function is always increasing or always decreasing. Now, it could happen that we increase, you'll see here an example for a little bit, but then once we start decreasing, we're like, okay, since I'm monotonically decreasing, I am good to go after that certain point. So we're going to use this theorem to look at a couple examples. The examples do get a little bit messy with some new proofs. So just take a big deep breath and you are going to do just fine. All right. So let's look at 4 to the n over n factorial. Additionally, if you have never seen what that exclamation point is, that's the factorial sign, and that means take the number that n is and multiply by all numbers smaller than it. So first we want to know, is this bounded? Well, let's look at a couple pieces of this and see. So let's plug in 1, 4 to the 1 over 1 factorial. So that's 4 over, we just say times 1. 1 factorial is just 1. So that's 4. I then get 4 squared over 2 factorial. So that's 16 over, this is 2 times 1. 16 over 2 gives me 8. So it seems like right now that this is going to be an increasing sequence. Let's look. 4 cubed over 3 factorial. So that's 64 over 3 times 2 times 1. 64 over 2, those two cancel and I get 32 thirds. 4 to the 4th over 4 factorial. 4 factorial would be 4 times 3 times 2 times 1. Well, one of these cancels with one of those, and then notice I get the exact same number here, so it's going to end up being 32 thirds. And actually from this point forward, if you continue with this pattern, you see that you start to decrease. So even though I have this little bit of an increase, I do end up 32 over 3, 32 over 3, and then I do decrease down to 0 over time. So we know that this is going to end up being decreasing, but how do I actually prove that? This is how you actually prove decreasing. I need to show that a sub n plus 1 is always smaller than a sub n. The next term in the sequence is smaller than the one before it. If I plug in n plus 1 everywhere where I see an n, that's what I'm trying to prove, then I get that this is 4 to the n times 4 to the 1 using exponent rules here. And remember, this is n plus 1 and then times all of the counting numbers below it, so n plus 1 times n minus 1 times n minus 2 until I get down to 1. Well, one thing that we can do is we can say this is n times 1 then times n factorial. Notice that this right here is a sub n. So this is 4 over n plus 1 times a sub n. And if you take numbers and divide by n plus 1, you are going to be smaller than a sub n over time. Okay, it's not until those n plus 1 numbers get bigger than 4, okay, that starts to happen. But once we get that we're 4/5 and then 4/6 and then 4/7, right? Those numbers times a sub n would be smaller than a sub n. That tells me that a sub n is decreasing, okay? And all of these numbers, when I'm plugging them in, I'm going to get a positive over a positive, right? So these are always actually greater than 0. So I'm bounded below by 0. Therefore, this series, or the sequence, excuse me, must converge. And the limit that it converges to is 0, because I have numbers that keep getting smaller and smaller and smaller, but stay positive. So its limit is going to be 0. All right, let's look at B. So now I have a recursive sequence. I know the first term is 2. But then I find the next term by plugging that in everywhere I see a sub n. So to find a2, I'm going to plug in the term before it here. So that's 2 over 2 plus 1 over 4. That ends up giving me 5/4. 1 plus 1/4 is 5/4. Okay, the next term, I then plug in 5/4 over 2 plus 1 over 2 times 5/4. And that ends up giving me, I believe it's like 41 over 40. And so if you notice, we're at 2, and then we're at a number a little bit bigger than 1, and then we're at a number, again, a little bit bigger than 1. And as you keep getting these, we find that we are getting closer and closer and closer and closer to 1. So bounded above by 2, bounded below by 1, which I think is the limit, but let's just make sure that this is monotonically decreasing. So I have to figure out, is a sub n plus 1 always less than or equal to a sub n? So it's going to feel a little bit like some magic, but here's something that I know. I know that my a sub n terms are always greater than or equal to 1, right? I figured that out. Oops, sorry about that. I figured that out over here. Well, then it must be true that if I square these, like if I square both sides, right, which this is 1, that must be true as well. If you're like, well, where are you going with this? Just stick with me, okay? If I add a sub n squared to both sides, then I get that a sub n squared plus 1 is less than or equal to 2 a sub n squared. And then if I divide everything by 2 a sub n, I end up getting a sub n squared plus 1 over 2 a sub n is less than or equal to a sub n. And this is a fancy way of this. Now, would you need to do this on your own? No, this is an example, okay, of how you can show that this is a monotonically decreasing function bounded below by 1. I would give you hints. If you're in my calculus class, I'd give you hints on where to go on this because you are very, very new to proving. But this does show that a sub n plus 1 is always less than or equal to a sub n.